Hello and welcome to this lecture number 2 of week 2 of the course on control engineering. My name is Ramkrishna. I am a faculty of electrical engineering at IIT Madras. In the last lectures, we saw how different or how signals kind of transform or the flow of information is captured via signals passing through different blocks of the system. And these signals also gave us a little indication of how a system would respond to a signal. So there were examples where we started off with a system that was open loop, unstable, and we could make it stable via feedback. There are also examples where we saw effect of disturbances. There are also cases where with the help of feedback, we could negate the effect of disturbances. There are also instances where I wanted to go from 0 to 1, but the system just stops at 0.9. And this we quantified as the steady state error. So later in this course, or much of this course, we will look at much more detail on how to design systems which will make an open loop system, open loop unstable system to a closed loop stable system. Also look at how will we how will we negate the effect of disturbances and so on. So to begin with, we will just do a little bit of recall of what we did in our signals course. In particular, in this lecture, I will focus on the concept of convolution and the convolution integral. Before that, we quickly look at the time and frequency domain characteristics of a system. And much of the course would be kind of divided into two parts. One is in particular to the time domain analysis, and second would be with respect to the frequency domain analysis and also design. A time domain graph shows how a signal changes over time. In the time domain, the magnitude of the signal as at each t is represented. Just say I take a signal of this form, sine of t plus 3 plus 2 sine 2t. So I can compute its values at different instances of time t equal to 0. I have 0.86, t equal to pi over 6, I have some other value 2.73, and pi over 2, I have 0.5, and I can compute its value at each instance t. Frequency domain graph, on the other hand, shows how much of a signal lies within each frequency. And all we know from our previous analysis on Fourier is that the signal can be represented as sum of different sinusoids at different frequencies, and each with a certain magnitude and a phase shift. So let us start with this example and see what does a frequency domain representation of this particular signal mean. So to start off, so I have in this uh, uh, in this particular signal, I have two components. I can write the signal as sum of those two individual signals that we had. That was sine t plus pi over 3 and then sine 2 of t. Now, if I, okay, so my standard representation of signals which I would borrow from my earlier notation would be a sine omega t plus phi. So omega deals with the frequency, phi deals with the phase shift, and so on. Now, if I look at these two signals, I can easily say that this signal, if I can use the word, repeats itself twice as fast as the first signal. So I have two different frequency components here. One is, or you can see, look at the frequency here is the frequency of sine 2t is twice as that of sine, just say t. I'm not worried about the pi by 3. So I have two frequency components here. One at 1 over pi, representing representing this signal. Second, 1 over 2 pi, representing sine t plus pi over 3. And similarly, I have a phase plot 1 over pi, so there is no phi here, and the second component has a phase shift of phi over 3. So this is like the frequency domain representation of my signal, which was originally it was sine t plus pi over 3 plus 2 sine 2 of t. Okay, I go a little more complicated signal, right? So I have like several components here. The time domain looks a little more messy to analyze. Whereas the frequency domain, I can largely look at how many frequency components. I can say look at the first signal has a frequency of 50, second has 120, 250, and all the way till 400. And these four are beautifully captured in the frequency domain plot. And similarly, I can also do for the phase shift, except I think this signal, none of them have a phase shift here. A little indication of how different representations of signals help us visualize in different ways. Okay, so to begin with, what could be these basic test signals, and why are these useful also? If I look at an unit impulse, so by definition, this is a signal denoted by delta t, which is non-zero only at t equal to 0 and integrates to 1. So how do I visualize this? So this is on the time axis. I have this rectangle of delta and 1 over delta for which the area equals 1. Okay, and if I just take the limit as delta going to 0, I will have a signal which has kind of like a zero width and like infinite length, so to speak. But a better way of mathematically writing this is to simply say that this is a signal which has an area equal to 1. Okay, what does this mean in terms of a physical system? If I look at, so for example, if I just take the example of a linear or of a simple pendulum, if I just give it a little perturbation or a little push, this the response of this to this system can be largely represented by what is the response to the system as an impulse. So this particular perturbation which I give it can be treated as an impulse, and I can compute the response of the system to the particular input. Similarly, a unit step is a signal that is denoted by ut and is defined as follows: that it has for t less than 0, it just takes 0 value. For t greater than 0, it has a value of 1. Just like I switch on a fan. So until just before I switch on, the voltage is 0. Just immediately after I switch on, the voltage goes to 230 volts, and the system responds in its own way to the 230 volts. Like a bulb glows immediately, a fan takes some time to achieve its full speed, and so on. Okay, so what is fascinating here, and how do we derive in general what is called as the impulse response to systems? So let us maybe look at a bit of a discrete time version of this. In discrete time, I would have say I have say a unit step which is defined as taking a value of 1 for n greater than or equal to 0, takes a value of 0 for n less than 0. Pictorially, I can just write it as say this is my t equal to 0, so this is all signals of length 1, starting at t n equal to 0, 1, 2, and so on. Okay, now if I do un minus 1 will be 1 for n greater than or equal to 1 and 0 for n less than 1. This is just the impulse delayed by one time step. How will that look like? If I just draw it here, this will be 0 until n equal to 1 and then start over from here and then keep continuing. Now if I do a un, sorry, if I do a un minus un minus 1, I get a signal which now looks like this. So I just say this minus this, so I just have something at 0 and everything else goes to 0 here. So there's nothing on this side and nothing on this side. This I will define as the unit impulse in the discrete time domain, which has a definition that u of n is 1 when n equal to 0 and 0 otherwise. Okay, and this un minus un minus 1 is called the first difference or something. Okay. Now I can make a similar analogy and see what is the notion. So here I have some kind of a notion of differentiation, right? So if I do a similar analogy, I must be able to say that my uh, impulse should be some kind of a derivative of a step. Of course, the problem arises because there is a discontinuity at t equal to 0. And this function I cannot differentiate. However, what I do is I look at this is function like this and I take a little interval here, delta, and I call that the unit impulse. Now I would look at as a derivative of u of delta as delta goes to 0. Okay, why is this true? Now, if I take a derivative of this function, this is allowed, right? And then this is like a slope of delta. So the derivative of this function now turns out to be something like this. So I start from here and I can just say, well, this is how it looks like. The derivative of this function is such that it is 1 over delta for this interval from 0 to delta, or and it is 0 otherwise. So there's nothing on this side, there is nothing on this side. Okay, this is now in my familiar territory, right? So I can now say that let me choose the right color. Okay, this I can say now as I can look at the derivative as u goes to 0, sorry, as delta goes to 0, that looks very nice. So this is 1 over delta. As delta goes to 0, this becomes like infinitely large values. And of course, the area still becomes 1. So I can write now that delta t is the derivative of u of t. Or in other words, u of t is also something like this. A nice relation between the impulse and the step functions here. Okay, other kind of signals we could look at is a ramp signal, which is kind of just increases with time. Mathematically, it's like okay, I think this should be a t. Okay, so a signal denoted by r of t is defined as for t less than 0, it is 0, and for all others, it's just t. At a signal with just slope of t. You could also have other kinds of signals with parabola and so on. Okay, now my idea here would be to see I have a system, I'll slowly start calling it P, and I subject it to some signals. So a signal could be as simple as an impulse. Okay. Now, from the signals course, I would not really go into details of this. I can represent any signal as a linear combination involving like delayed impulses. So a signal x of t can be written as an infinite integral like this. Okay, now this is useful because I can look at how system responds to a certain signal. So if I denote by this as the impulse response, when I say impulse response is how does the system respond to a particular impulse occurring at a particular time t. So if I denote h tau at t as the impulse response due to an impulse occurring at time t, then I can exploit the property of linearity. What is the property of linearity? That the response due to a linear combination of inputs is a linear combination of the responses. Largely, this the superposition, right? So now I can write y of t, the entire response, not just for impulse at tau t, but the entire response can now be written uh, from superposition in this way. Okay, now again, what we know is that uh, from the theory of linear systems is that I exploit the delay property that the response to an impulse at time t is the same as the response at zero shifted by time t. If you look at the time shifting property also that we talked about in linear systems, this is a property of time invariant systems. Right? That the response to a system at time tau is the same as response to the system response to an impulse at zero shifted by tau. So it doesn't matter if I shift the input or I first measure the output and shift the output by a certain tau. Okay, so this is now mathematically written in this nice beautiful expression called the convolution integral, and largely captures the response of a system to different kind of signals. Okay, so this convolution is a mathematical way where I combine two signals to get a third signal. So the convolution of x and h results into this nice looking integral here. Okay, don't worry about why this thing. This has a very good graphical interpretation of this. And this convolution is used to express the relation between input and output of a LTI system. Again, this thing is important because all these two properties or we arrived this by using two things. One is the superposition here, and second is the time invariance of systems here. Okay, so this convolution, it relates the input uh, of the system ht to its output y of t. It's not just a little multiplication that h times t times x of t. Okay, so before we see a graphical interpretation, let's just look at what this actually means, and then what are the several properties of this, or maybe we'll come to the properties a little later, and before we'll just look at how this things respond. Okay, so the convolution of with an impulse. So if I take a signal x of t and I convolve it with just delta of t, then it's just nice. So I just recover the original signal. If I look at as the same signal, I convolve it with the impulse with one step delay, then it gives me a signal uh, which is just delayed, the same signal delayed by that appropriate time. So I can write a general property now is that if I have a signal x of t with a convolve with an impulse delayed by t naught, this will just be the signal delayed by appropriate amount of time, and if there is no delay, I just recover this particular signal. Okay, so we'll try to visualize why this particular thing is happening. So we start off. Let's say I take a convolution of two step signals, and what I essentially do is my formula. If I just write it down, so x convolved with h would be, so x times h will be integral negative of infinity to infinity x of tau h t minus tau d tau. Okay, now here I have two signals. I have u of t and also u of t. Okay, so let's see what is this. So this is I take two signals here. First is so this will be u of tau, u of t minus tau. Okay, so how do I plot each of this? U of t is just nice. So this is u of t uh, having one the magnitude 1 from t greater than or equal to 0. Okay, now I look at u of t minus tau. So what I do is I just shift it. So this is u t minus tau. So what this does is I am integrating this from minus infinity to plus infinity. Okay, and then looking at the area spanned by the product of these two signals. So if I just look at these two terms, and this kind of just keeps moving, right, as tau increases, and we just look at the area. So until I reach t equal to 0, the area is 0. So I can say u with u is equal to 0 for all t less than 0. Okay, so for t greater than 0, let's say I take some value, Okay, we use this pen. Okay, at t equal to 0, I'm here. Okay, and then at say t equal to say some other value, I just keep moving in this direction. Okay, so this is say at a particular t, say t equal to 1, and this is at t equal to 1. So I'm just looking at what will be the area of these two. That will just be so integral from 0 to t. If I just take any arbitrary t greater than 0, 1 comma 1 d of t, or say d of tau. This will just give me t. So u convolved with u will just give me the ramp signal r of t, which was defined as this was equal to t for t greater than 0 and 0 otherwise. Okay, now similar analysis I could also do for the step, right? So for the convolution of these two steps. Um, so I just look at, so delta tau, I have this signal here. Delta tau I can write neatly as uh, so so this delta tau, so this, if I just see how the convolution works, so this is my so I'm looking at x of t delta t minus tau. So somewhere here, maybe it's a delta t minus tau, and it just moves towards the right. So until t less than 0, sorry, until t less than 2, nothing happens. Once I reach t equal to 2 and I keep moving right, the area will be just the magnitude of this one, which is 0.5. And because my delta equal to 1 and is scaled by this magnitude here, which is the magnitude of x of t. So from here all the way till my delta reaches here, it will just be 0.5, and after that it again goes to 0, like here. Okay, same thing happens in the second case, just that now it is delayed by, so this is delta t minus tau. Now this is delta t minus 1 minus tau. So this expression, in this case, a delta reaches at t equal to minus 2, if I may say so. But here it will reach like a second later. And everything, therefore, that we compute will be delayed by 1 second. And the result would be that the convolution will have 0 until for t less than 1. It will hold a value of 1 for the duration. So on the right hand side also it will be delayed. Here it ends at 2, here it ends at 3, and for all other values it will be 0. This is nice. So we'll just now quickly read out some properties. So the commutative property convolution of x1 versus and x2 is the same as x2 with x1. We'll still have the distributive property. I'll not read out this loudly. You'll have the associative property, the time shifting property. We saw this in a little bit of with the impulse response. That will be true. I mean, even if the both signals are shifted by time t0 and t1, the output will be totally shifted will be shifted by a overall time of t0 minus t1. And lastly, if I have x with a, then the time scaling or the scaling property will just hold a value which will look like this. Okay, let's do one more example to understand our visualization better. So here I will have two signals. I have x of t as e power at u of t with a greater than 0. So this u of t will ensure that the signal has values only from t greater than 0. And then my h of t will be u of t. And I need to check what is x convolved with h. So this will, in standard, I will be looking like the integral of negative infinity to infinity x of tau h t minus tau d tau. Okay, let's plot each of these individual signals. Okay, uh, so the h of t is a unit step. So this will be my h of tau. X of tau is e power minus at ut starting at t equal to 0. So it will start from here, it's taking a value of 1 at t equal to t equal to 0 and so on. Now I need to look at this signal h of t minus tau. H of t minus tau, I just shift it towards here. This is h of t minus tau. This is, and I need to look at what happens to this if the signals moves towards right. So for t less than 0, the product of x of tau and h of t minus tau is 0, which also means that for t less than 0, y of t will also be equal to 0. Okay, things will change when for t for tau greater than 0. So which means so my signal will kind of reach here and then keep kind of moving towards the right in this direction. So at 0, so the value will be 0 because the area is 0, and slowly my area will start building up. So if I just kind of superimpose my plot here, the area will slowly build up in the following way, and after it reaches this point, it will just try to stabilize or just be to some constant. Okay, let's work out what this constant would be and how to visualize this. So I know that now this y of t with this expression would simply be 0 to t e power minus a tau d tau. Because h is simply 1. So this will turn out to be, this is 1 over a, 1 minus e power minus e tau. So this value, so it will start with a value of 0 and eventually reach a value of 1 over a. So it's bt. Okay, so this is how to one way to directly compute and also check via the visualization. Before that, I'll just also show a little video of how F convolves with G and how the yellow line represents the area from minus infinity to infinity of the product of F of tau and G t minus tau. Okay, to summarize, we have looked at time and frequency representation of signals and also looked at the convolution integral and how it helps us study response of a certain system to certain input signals. Of course, it's not always easy to compute complex integrals or even to visualize graphically. So are there easier tools which will help us do things faster and in a more elegant manner? That will come up in the topic of Laplace and inverse Laplace transforms. Stay tuned. This will come up in the lecture of lecture number 3 of week 2. Thanks for watching.